Welcome to the Explainer. Today, we're going to decode the magic behind every single digital photo you've ever taken. We're talking about that incredible journey from a flash of light in the real world, through the lens, and finally into a file on your screen. And what's really cool is how much this whole process mirrors our own biology. All right, let's jump right in with a little test. Take a look at these three squares. Which one of the inner squares looks the darkest to you? Go on, take a good look. Got your answer? Okay, hang on to that, because it's the key to, well, pretty much everything we're talking about today.
So to understand how a digital camera works, we first have to look at the original camera, the most powerful one ever built. And that's the one right inside your head.
You know, the parallels between your eye and a camera are just amazing. Light comes in, our lens focuses it, and boom, an image gets projected onto the retina at the back. The retina is basically a biological sensor, grabbing all that incoming light.
And this biological sensor, the retina, it's absolutely packed with these things called photoreceptors. You've got two kinds. First, you have the rods. We're talking up to 150 million of them, and they're for seeing in dim light, kind of like your built-in night vision. Then, you have the cones, about 6 or 7 million, and they're the ones that handle bright light and let you see the world in brilliant color.
Now, with all that incredible tech packed into our eyeballs, you'd think our vision is perfect, right? Like a flawless video recording? Well, let's circle back to that first question I asked you, because the way our brain processes what our eyes see, it has some, let's call them quirks.
So what's the answer? Get this. All three of those inner squares are the exact same shade of gray. No, really. If you don't believe me, just use your finger to cover up the backgrounds. It's a classic illusion called simultaneous contrast. What's happening is your brain is changing how it perceives a color based on what's around it. It's not just reporting raw data, it's giving you an interpretation.
And our brain's little editing tricks don't stop there. Take a look at this. Each of these vertical bars is a totally solid, uniform shade of gray. But I'm willing to bet you see a slightly brighter, almost glowing band on the right edge of each strip and a darker one on the left. That's called the Mach band effect. Your brain is basically enhancing the edges for you, trying to make the contrast pop.
And it just keeps going. Our brains are constantly filling in blanks, creating shapes that aren't actually there, or totally misjudging things like length and angles. So what does all this tell us? It tells us that what we call seeing isn't a passive recording of reality. It's an active process of construction.
Okay, so if our own vision is basically an interpretation, that leads to a huge question. How in the world did we teach a machine to see? And does it fall for the same kinds of tricks?
Well, it turns out the basic process for a machine is surprisingly similar to our own biology. In both your eye and a camera, you've got light bouncing off a scene. That light gets focused by a lens, and it hits a sensor. That sensor's job is to turn the light into an electrical signal.
But here's the thing, just capturing that signal, that's only half the battle. The real trick, the absolute magic of digital imaging, is figuring out how to take the continuous, infinitely detailed analog world and stuff it into a finite, neat and tidy digital file.
I mean, how do you even do that? How do you take the smooth, flowing reality all around us and represent it with just a bunch of numbers? Well, the answer comes down to two key steps. These two steps are the foundation of every single digital image you've ever laid eyes on.
Okay, so first, imagine you're a camera sensor scanning across a single line of an image in the real world. You're not seeing pixels yet. All you're detecting is this continuous, kind of messy, analog wave of light intensity going up and down. So to make sense of that continuous wave, the camera has to do two crucial things. First up is sampling. That's where it digitizes the coordinates. Basically, it breaks the image down into a grid. And second is quantization, where it digitizes the brightness. It measures the brightness at each point on that grid and gives it a specific number. Let's break that down.
Okay, so sampling. Think of it like laying a piece of graph paper over the image. The camera only takes a measurement of the light at very specific, evenly spaced points. Each one of those little samples you see there is a single measurement taken from that continuous light signal. But even those samples can have an infinite range of brightness. That's where quantization steps in. The camera basically decides on a limited number of brightness buckets, in this case, just 8 shades of gray. Then, for each sample, it just rounds the value to whichever shade is closest. It's forced to pick one. And what do you get when you put sampling and quantization together? You get this, a digital image. And it's really nothing more than a big grid or a matrix of numbers. Each number in that grid represents the brightness for one tiny square of the picture, a single picture element, which we all know as a pixel.
All right, so now we have our grid of numbers. How good that photo looks, its quality, really boils down to two things: spatial resolution and intensity resolution.
Let's make this simple. Spatial resolution is just how many pixels you have. It's the size of your grid. The more pixels, the finer the detail you can capture. Intensity resolution, on the other hand, is how many shades each of those pixels can be. It's like your digital box of crayons. The more shades you have, the smoother and more realistic everything looks.
And you can really see the difference. Here's what happens when you mess with spatial resolution. As we drop the number of pixels way down, from a 256 by 256 grid to a tiny 32 by 32, the image just gets super blocky, right? We're losing all that nice fine detail because our sampling grid is just too big and clumsy. Now here's what happens when you reduce the intensity resolution. As we go from having 16 different levels of gray all the way down to just 2, pure black and pure white, you start to see these harsh, unnatural-looking bands. That's called false contouring. It's what happens when you don't have enough shades in your palette to create a smooth transition.
So, when you think about it, from the optical illusions our own brains create, to the sampled and quantized grid of a digital file, we've seen that no image is a perfect, one-to-one copy of the world. Our eyes interpret, digital cameras approximate, and that leaves us with one last, kind of mind-bending question to chew on. If every image we see is just an approximation of reality, what does it even mean for a photo to be real?